Hi, my name is Isaiah Roberts, and I'm going to be talking to you about the reanalysis of possible shorelines in the Arabia Terra region of Mars. So, the question I was trying to research was whether or not Robert I. Citron's reasons for the deformed status of the shorelines were accurate. But before I get into that, let's talk about what shorelines actually are. As of today, there's no concrete evidence that proves that Mars once had water. Concrete refers to solid and irrefutable evidence. However, there is a lot of evidence that strongly insinuates that Mars once had water. To be more specific, the study of paleoshorelines, which examines ancient shorelines using geology, archaeology, and ocean research. By definition, shorelines are the lines in which large bodies of water, such as oceans and lakes, connect with the land. The significance of this is that where there are shorelines, there is also water. Shorelines have specific or signature characteristics that can be used as evidence for identifying them. Examples of these include volcanism, glaciation, and impact events. The word for this study is that where there are shorelines, there's a very good possibility that there was also water there, and proving water on Mars would be a big step for this field. Here is a global view of Mars from the top. So the distinct white lines towards the top of the globe are the proposed shorelines by Parker. The two main shorelines, which are the Arabian and Reanalysis, are going to be the longer, sort of like the longer outlines that are circling. The middle of the globe, which the lines are encircling, is going to be the possible primordial ocean that Mars once had. So the position of the shorelines can also be used to show the age of them. So since the Deuteronesus shoreline is being encircled by the Arabian shoreline, the Deuteronesus line is going to be younger than the Arabian shoreline. So for the topography models of Citron's paper, there were abnormal variation in these models. As seen in the figure to the left, when comparing the current shoreline topography to the present paper, the difference in elevation are clear. Reasons for the variability are unknown, however, it was inferred that the data points weren't accurate with the proposed shorelines found previously. These proposed shorelines and arc maps, which is going to be the figure to the right, in the figure, the colors represent different elevation levels, and the green dots give an outline of the proposed shorelines. The problem is the accuracy of these green dots. After tracing each dot, you can see how some dots aren't even on the proposed shorelines and are just sitting on random craters. This may seem insignificant, but it could lead to elevation data with abnormalities like Citron's elevation data. Thus, at Hopkins, my main goal is to either prove or disprove Robert I. Citron's shoreline paper. Citron's Starship shoreline paper explains that the reason for the proposed shoreline's non-equipotential properties is volcanotharsis, specifically through the emplacement of tharsis by true polar wander or TPW. The problem with Citron's Starship shoreline paper were the elevation values that he used. His elevation data show no evidence of an equipotential surface, as I stated previously, and does not support the claim of having shorelines. Furthermore, in order to prove or disprove Citron's Starship shoreline paper, I would have to plot the elevation data of the proposed shorelines myself. This was accomplished through photogrammetry, which is the science of making measurements using pictures or photography. This will be one of the most efficient ways for analyzing elevation values on Mars, since photography is one of the ways to get high-quality samples from Mars. Specifically, the camera that was used for the photogrammetry was the CTX, or contrast camera, which is shown in the figure above. The CTX camera takes pictures of Mars from about 400 kilometers above it and is connected to satellite. First, I use instruments such as JMars, ASU Mars, and Google Mars to look for DEMS of proposed shorelines. In order to closely analyze proposed shorelines, I look for stereo pairs. Stereo pairs are two aerial pictures taken from different positions to give a stereoscopic effect, which is just a more enhanced picture when viewed. One of the base requirements for a good serial pair is to have an emission angle difference of 10 degrees or more. The emission angle is the angle between the spacecraft and a vector drawn perpendicular to the planet's surface that the spacecraft is viewing. Next, after I found about 5 good serial pairs, I started to make them so I could analyze the serial pairs. I made these DEMs using Unix, which is a multi-user, multitasking operating system. Basically, I use Unix programming to make DEMs. This process took about 3 to 4 days. And DEMs are digital elevation models, which basically just show the geography and topography of the perspective model. After making the DEMs, I load a MOLA, which is the Mars Orbital Laser Altimeter, data into ArcMap, which is a geospatial processing program. When MOLA is loaded in, it is basically loaded in a map of Mars. After loading the MOLA, I uploaded one of the stereo pairs that I created into ArcMap. The way this works is that the stereo pair, which is an image on Mars, will load in and overlap on the MOLA data, which you can see on the right figure. Finally, I use a shape editor tool on ArcMap to trace the shorelines of my DEM so I can measure the elevation values for it, which you can see on the figure to the right as well, which is why there are black outlines sort of on the craters of the two DEMs. Next, I interpolated data, which is basically turning my tracing of the shorelines into elevation values, and actually turning those elevation values into a figure. In order to do that, I use MATLAB. So I basically transferred my data over from ArcMap into MATLAB, and I coded it in a way for it to show a figure of a XZ view of my data, with the x-axis being the distance in meters and the z-axis being the elevation value in meters. So here are my results. For the figure on the left, it consists of my personal data plotted. All of the interpolations of the specific parts of the shoreline that I did are graphed into a figure of an XZ axis, with the x being the distance along the shoreline in meters and the z being the elevation value in meters. As you can see, this graph isn't straight, so it does not show an equipotential surface, and it in fact fluctuates. As for the figure to the right, it consists of the comparison of my personal data, which is going to be in the red, to Citron's elevation data, which is going to be in the green. This XZ view of my data shows a more fluctuation in elevation values compared to Citron's elevation data at that point. My elevation data fluctuates around 450 meters compared to Citron's data, which is relatively more flat at that point. This implies that Citron's elevation data was not precise at that point on the shoreline. And since these current results still show a non-equipotential surface, it would be better to collect more data. Human error could potentially limit the accuracy of my data, since I manually traced the shorelines on ArcMap using a cursor. However, its influence isn't great enough to influence the analysis of my results, and is still a major improvement over the MOLA data used previously. To conclude, I found that the putative shorelines show non-equipotential features on a small scale based on their fluctuating elevation data. My results show a non-equipotential surface. However, the standard deviation of the variation in the elevation data is significantly more than Citron's elevation data. This direct comparison of the current data and Citron's data proves my previous hypothesis of Citron's claims for the reason behind the shoreline's deviation from constant elevation or an equipotential surface not being fully accurate. This also shows that Citron's data was not poorly sampled, but that the shorelines truly don't follow non-equipotential surfaces at a small scale. When I re-examined the shoreline data on a small scale and plotted it alongside Citron's data clearly showed a tilt in different areas along the shoreline, which can be seen in the previous figure. Lithospheric deformation can only cause a general tilt in topography at large spatial scales, which is why Citron used lithospheric deformation to prove his model of large-scale elevation fluctuation. However, lithospheric deformation cannot be used to prove small-scale, non-constant elevation due to the fluctuating values at different parts of the shoreline. My results also concur with previous research, which states that the proposed shorelines have non-equipotential surfaces. As for future research, I plan to examine the topography of other shoreline features in other parts of the northern Arabia, Terra, and the Deutero-Nilo shoreline, and possibly the Isidis shoreline. As for my acknowledgments, I'd like to acknowledge Olin Hall of Johns Hopkins University and Dr. Kevin Lewis, my mentor, for giving me the opportunity to research this very interesting topic. I'd also like to give props to Andrew Annex for helping me out and give me a couple tips when using ArcGIS. I'd also like to acknowledge the Ingenuity Project for giving me the opportunity to research, and my research coordinator, Dr. Rosen, for everything that she's done for me during this research process.